My name is Kanna, so I work on turbulence, and in this talk I'll focus a bit about introduction to turbulence, the classical turbulence, the Kolmogorov theory of turbulence a bit. Yeah, quickly move on to how is it different in the context of geophysical fluid dynamics. So turbulence, I'm sure you would have already seen many examples, so it's all around us in a sense. So here I show some typical pictures where I look at turbulence in a plume, and then you have turbulence behind the wake of an airplane. Here you have turbulence that is being driven at the scale of a cyclone, and then finally you have turbulence which is driven at the level of the solar flares, so driven by magnetic fields. So in all these examples, you can see that the length scales of turbulence, they go from of the order of maybe a few tens of centimeters to a few meters, to few tens of meters, to about kilometers, and few hundred kilometers length scale to thousands of kilometers. So you can see that as we vary the length scales, the phenomena of turbulence is ever present, right? And firstly, we see that it's a very chaotic, complicated motion, right? So you have a lot of processes that is very difficult to model them analytically, right? Unlike laminar flows where you can do a lot of things, asymptotics and all. In turbulence, you cannot get exact solutions, you cannot do exact predictions, which are very difficult, right? And so given this complicated problem, why are we interested in studying them at all, right? I mean, we know that they are there, but why is it important, right? So some of the main characteristics of turbulence is that they enhance your mixing and diffusion, right? So if you have done this diffusion of tracer particles in a fluid experiment, you would see that if you just put, or even let's say if you open a perfume in this room, you would see that a time scale of diffusion, if you do not have any kind of AC or any kind of fan that is going on, the time scales of diffusion would be of the order of hours, right? Whereas if you have some kind of airflow that is present or some kind of turbulence, you have a time scale which is much shorter. So in a sense, you have a typical, usually the diffusion in the absence of any flow is driven by what is known as the diffusivity coefficient. And in a turbulent setting, the diffusivity coefficient, which usually is modeled to what is known as an eddy viscosity type modeling, is can be modeled by the typical velocity times the typical length scale, right? And the time scale for diffusion, let's say momentum diffusion for an eddy type process, so that's L square over UL. And if you compare it with the viscous diffusion, which is L square over nu, you would see that the time scale for the viscous diffusion is very much larger than the time scale for the eddy diffusion, right? And the time scales related to the Reynolds, if you just take a ratio, you see the Reynolds number naturally occurring. And when the Reynolds numbers of these systems being very large, you would quickly see that the necessity of having an eddy diffusion is very much important to understand mixing. So here there's a simple video of this Kelvin-Helmholtz instability that somebody was asking about. So you have two layers of fluid, and in the absence of any instability which leads to turbulence, the diffusion is very weak. Whereas once you set in turbulence, you see that these two fluids, they start mixing very well, right? And in the below image, so this is something which I obtained from Wikipedia, and this is something which I obtained from the YouTube channel, where they study Rayleigh-Bénard convection, so 2D Rayleigh-Bénard convection. So in the turbulent regime, you start to see the mixing of the cold fluid which is dropping from the top in blue color and the hot fluid which is in the bottom. So turbulence drives mixing and diffusion at a much more faster accelerated pace than what you see in normal viscous diffusion cases. So turbulence is very much necessary for these processes. And the dissipation, so a lot of questions about what happens to the energy which is being injected at the tidal frequencies. So the dissipation by turbulence is in a generic turbulent kind of system or fluid which goes to turbulence. We know that the dissipation is not negligible, right? So if you consider some kind of a laminar flow, if you do not consider any forcing from the boundaries, the typical dissipation of the fluid is given by viscosity times the gradient of the velocity field whole square averaged over the volume, right? So this is the dissipation in the bulk of a turbulent of a general fluid flow, and in the laminar case, right, when your velocity fields are well behaved, what you can find is that as viscosity goes to 0, d tends to 0, right? So this is something that is well known for laminar flow. You can do the exact solution and find it yourself. So the dissipation goes to 0. Whereas in a turbulent situation, what happens is that the velocity fields and the gradients, they also scale with the viscosity. And this is a very famous diagram, which is the drag coefficient diagram. So for very low Reynolds number, right, in the laminar case, the dissipation, the CD is just a dissipation over some non-dimensional number. So d by u cube over L would be your CD, the drag coefficient. So in the low Reynolds number limit, you see that this thing goes to 0 in the limit of large Reynolds number, which you expect when nu tends to 0, right? But as Reynolds number increases, you see that it is an experiment of flow past cylinder. Let's say for very large enough Reynolds number, the flow behind the cylinder becomes turbulent, and the dissipation starts to depend on these smaller scale structures, and you can see that the dissipation coefficient goes to a constant. And then there's an interesting phenomena of drag crisis, which I won't talk about. And then again, at very large Reynolds number, it again goes to a constant. So in a sense, we see that the dissipation, unlike a laminar flow which goes to 0, it goes to a constant. So what does it mean it goes to a constant? It means that the dissipation is independent of the viscosity, right? Sorry. So dissipation being independent of the viscosity as nu tends to 0, right? So this is a case where nu equal to 0 and nu tends to 0 are two different solutions altogether. And then there are some, so this is the video of Rayleigh-Bénard convection. You can see this strong mixing between the cold and the hot fluid. And then the other interest are, so these turbulent flow, they can lead to very strong fluctuations. So some of these fluctuations of interest, like extreme events. So here I show waves on the surface of the ocean, and because of some nonlinear interactions, you can have some localization and lead to some rogue waves and all. So there's a lot of interest in studying extreme events, even in the context of climate. So turbulence leads to all these different phenomena, and understanding turbulence helps us to at least understand certain of these things which we see here. And in the geophysical context, so they are present in literally every system that you look at, just because of the length scales which are involved in the system. Just so here I show water waves, so gravity waves, capillary waves at the surface of the ocean, the interactions which lead to strong turbulence. So you can also have breaking of these waves, which leads to important assay interactions. This exchange of carbon dioxide between air and sea could also be possibly driven by such processes. And then the oceanic circulation, which again, just because the typical length scales in the system can have important effects due to turbulence. And below is a typical picture of the atmospheric quasi-biennial oscillation, where in the mid latitudes you have this reversing mean flow which reverses. So these are driven by convection at the atmospheric boundary layer, which then excites inertia, internal waves, which then leads to such mean flow which is driven in the atmosphere. So you have this periodic, so this blue color represents I guess the plus direction, that color represents the negative direction, so east to west, west to east, and it has a very interesting period of 28 months. So it's not exactly a biennial oscillation, it's a quasi-biennial oscillation. And so where does this 28 months come from? What is the role of these turbulent fluctuations here? So these are all interesting questions that people look at. And so in the even larger systems, so in terms of GCM models, So a lot of phenomena are intrinsically related to this turbulent fluxes, like what happens in this QBO kind of processes. You have the small scale interactions which are important, and because of the problem that people are talking about in the morning, so you need a lot of grid points to resolve these small scale turbulence that is present along with these large scale structures. And because of numerical constraints, people resort to parameterization, right? So you kind of try to relate small scale fluctuations, some kind of Reynolds stress kind of tensors, you relate it to the background gradients through some effective viscosities, right? Like the eddy viscosity that I wrote down here. So you can also try to relate the fluctuations in the atmosphere, ocean systems, and try to relate it with background current and so on. So, so more of that later. So we see that turbulence plays a very important role in these systems. And is there a way to understand these turbulent processes, these small scale fluctuations, and how can we go to modeling such turbulent phenomena, right? So I go to the standard picture of turbulence. So this, I'm sure, if people have taken a course on standard turbulence, you would have already seen. And Jim was also talking about the Richardson picture. So the picture of turbulence that we currently understand is a phenomenological picture, right? So we don't have exact theory for turbulence. So it's more about understanding the typical, let's say, the mean and the fluctuations around which the system exists. So in the phenomenological picture, turbulence is generated at a length scale which is larger than the length scale of dissipation, right? So basic form of turbulence is that you have a length scale at which energy is injected, right? So if this is our length scale, right, we have energy that is being injected at some length scale, and what happens is that at these length scales, right, the dissipation effects are very small, right? So it's not getting dissipated. So what happens to this energy? And it so happens that in this system, at least in the three-dimensional isotropic homogeneous turbulence, which people understand to some extent, is that this energy gets cascaded to smaller and smaller length scales, right? So this big circulations, they get broken down into smaller circulations, and they pass on the energy, right? And you can estimate the dissipation of these lengths at these length scales. And the typical dissipation, because the length scales are over which they vary, are very large. So the viscosities being very small does not affect these structures. So you can, in effect, forget the fact that dissipation exists. So they get cascaded to smaller and smaller scales until they hit a scale where dissipation becomes very strong, right? So these are the scales over which this particular term becomes non-negligible, right? The local term, right? So gradients of the velocity field become non-negligible, at which dissipation starts to play a role. And this along this direction, along this cascade, you have energy that is getting transferred to smaller and smaller structures, and all along this cascade, you have this energy which is more or less constant, right? So it's not getting dissipated, right? And it's once it's injected at a particular length scale, it just gets transferred to smaller and smaller scales. So at a particular length scale, the system just looks at the energy that is coming at from above and just transfers it to smaller scales, right? So for a particular length scale in this, in between the forcing and the dissipation, the typical phenomenology says that the typical velocity fluctuations at those length scales can directly be related to the injected energy epsilon and the length scale and the local length scale at which it exists. So the typical relation would be, just by dimensional analysis, would give you delta U going like epsilon L to the power 1/3, right? Just from dimensional analysis. What is delta U? Just the typical velocity fluctuations over a length scale L, right? So, so using this phenomenological theory, one can go and start doing some experiments, and what one can see is that if you look at flow behind a grid or examples of homogeneous isotropic turbulence, where you are driving, let's say, a fluid in a homogeneous isotropic manner, like grid turbulence, or if you look at flow past a sphere but very far away from the sphere, or if you are looking at body force turbulence like MHT turbulence. So what happens is that the energy content at different length scales, they start to follow a relation which is not very far from the relation that I wrote. And there's this famous relation which is k to the power minus 5/3. This is the Kolmogorov theory of turbulence, right? So I won't go too much into the detail, but this is a short recap of the general turbulence theory. Just to note that an exact relation that one can derive is the Karman-Howard-Monin relation, or the 4/5 law of turbulence, which is an exact relation in this isotropic homogeneous turbulence, which states that the third order structure function that scales linearly with R. Right? So there are some exact relations that one can derive, and maybe some bounds which says that the dissipation goes to a constant. But beyond that, we have to do some phenomenology to understand it. Right? So, what do we do from there? So people have looked at all kinds of simulations. So these are some state-of-the-art simulations recently on 16,000 cube course. And this is Shea, Jackson, and Ozak in 1991, where they did a similar kind of simulations of 3D turbulence in a homogeneous isotropic box. I do not remember the resolutions, maybe around 512 or 1000 cube. And these days, in 2018, you can go up to 16,000 cube, which is a lot of points, right, along 3 directions. And it's not just a question of spatial resolution, as people pointed out. You also have to look at temporal resolutions. You have to also resolve the smallest length scales and time scales, smallest time scales in the system. So by doing all that, what can we do is that we see that 3-dimensional turbulence leads to the formation of very small filamental structures. Right? So these are vortex filaments. So these structures are vortices, right? Where you have you see that it's elongated vortex filaments which are present, and here you see the dissipation structures which are which show this phenomena of intermittency, which I will not go into details, which are corrections to the phenomenological theory of 3-dimensional turbulence. So these are pictures of homogeneous isotropic turbulence, but we know that in the atmosphere and oceans, anisotropy plays a very important role. So anisotropy, rotation, and stratification, as people pointed out, plays a very important role, and you do not see very small structures in the atmosphere, right? When you look at the atmosphere, you start to see these large-scale structures that firstly come out, and then you start to see these waves, right? So you have this phenomena which you do not see in this classical 3-dimensional turbulence. So where do they come from, right? So can we understand them from a turbulent perspective, right? So here's a nice photo which I took from NASA's website, where it's a re-entry of some, I think, some space shuttle, and then you see this light rays which are getting internally reflected and reaching you, and looking at, you can look at the troposphere, stratosphere, layers of the atmosphere with different densities, right? And what you see is that the layers, the thickness of these layers, right, are very much small as compared to the extent, right? So typical thicknesses are of the order of tens of kilometers as compared to the extent of the Earth. So the typical radius is of the order of 6,000 kilometers. So first question is, what does this confinement do to the turbulent structures that we looked at, right? What do they do? And secondly, as Jim and Mani pointed out, so the fluid that we are studying is basically subject to rotation and stratification, right? So these are not just 3-dimensional turbulence which is forced somehow. There's rotation and stratification play a very important role, and the non-dimensional numbers that one can construct point that they play a major role in the dynamics of these fluids that we will see later on, right? So a simple model to understand the formation of large-scale structures is the 2D turbulence model, right? So which will come back to in the context of quasi-geostrophic models. So here on top is an experiment of 2D turbulence performed by Joan Hero. So where they looked at thin layer of MHT turbulence. So basically you look at liquid metal in a very thin layer, and then you have currents which pass through the liquid layer of through the liquid metal, right? And then you have alternating magnetic fields, right? So by playing with the polarity, you can create J cross B currents, which will drive the fluid. So it's a fluid which contains charges, so it reacts to the Lorentz force. So J cross B will drive this fluid, right? And if the driving is very small, you can see this nice vertical structures. So there are some particles which are seeded, so you can see this vertical structures which are of alternate sign depending on how your magnetic field, your magnets are kept at the bottom. Right? So it's a very thin layer of liquid metal which is being driven by a Lorentz force, a magnetically forced system. And as we increase the forcing, right, so you amp up the current or you increase the strength of these magnets, you see that there's a route to turbulence, right? So there's a route to chaos and then turbulence. So it goes to some large eddy, so negative viscosity instabilities and so on. And finally, you go to a system when it's highly turbulent where you see a very large coherent structure, which is very much different from what you see in classical three-dimensional turbulence, right? So where does this come from? So this comes from, so what we see as later on as a phenomena of 2D turbulence. So here is a simulation done by some students of mine where they just took looked at the 2D Navier-Stokes equation, put a forcing and dissipation. I'm sure you can all do it very quickly if you learn some simple numerical techniques. And what you see is this positive and negative vortices which are moving around. So these are long-lived vortices, and they basically are very stable and they do not decay into any other smaller structures, right? So such large-scale vortices are found in 2D turbulence, and the main reason for that is that in 2D turbulence, along with the energy which is a conserved quantity, the vorticity, if you write down the vorticity equation, so in 2D the vorticity is a scalar field. Let's say some forcing and dissipation. So in the absence of forcing and dissipation, or when these are very small, we can show that the entropy, which is the spatially averaged square of the vorticity, is conserved. And what happens when you have an additional conserved quantity on top of energy is that you have a dual cascade, right? So entropy being the higher derivative, it goes to smaller structures. So one can show it using some triadic interactions, why entropy goes to small scales and energy goes to large scales. But that you can do it by yourself. But what is interesting is that this dual cascade leads to an inverse cascade of energy. So you have energy being accumulated at larger and larger structures, which is what you see in these diagrams, right? So in a standard three-dimensional turbulence, you have energy which is cascading to small scales. In the 2D turbulence picture, energy goes to the largest box. So it's also called as the condensation phenomena, right? And then you can study, again, you can do some phenomenology with these turbulent structures, like what you do in 3D turbulence. You can do some phenomenology, get some scaling, some power loss, and so on. So I let you to refer this recent review article where they have compiled all the results of 2D turbulence. Right? So from 3D turbulence, if you put confinement, we can readily see that these vortex structures, they start merging with each other. Right? This is what you see in that experimental picture. These vertical structures, they start merging and they form larger vortices, right? And lead to an inverse cascade of energy, right? And now what happens when you have rotation, right? So if you just have a rotating flow, what is known is that in the large rotation limit, you start to form these strong coherent structures. Right? So here is a simulation where we looked at rotating turbulence. So you take a three-dimensional box and you put global rotation to it, right? And in the rotating frame, you look at what are the vertical structures. So here's the vorticity field, right? So the blue represents the I think the positive vortex, and red represents the negative vortex. And you see this strong columnar structures, right? So in a sense, it kind of reminds you of this 2D turbulence, right? So this is at a particular instant. It kind of reminds you of this 2D turbulence kind of picture. And it's actually, one can show analytically that in the limit of large Reynolds number, and if you do not force any kind of waves in the system, you end up getting to some kind of a 2D turbulent phenomenon, right? So rotating flows by themselves also lead to some inverse cascade of energy, independent of any kind of confinement, right? So rotation does prefer uh, uh, formation of large scale structures. And why is it? So what chooses the direction along which it becomes columnar? So for that, one can just directly look at the vorticity equation in the rotating frame. Yeah, and when the rotation rate is very large, right, and you look at time scales and length scales which are also large. So these two quantities are much smaller than the rotation rate which is present here, right? So a dominant balance would lead to 2 omega dot grad u to be close to 0, right? So this is the Taylor-Prodman theorem, which you would have seen if you had gone to some basic books on GFD, right? So you have this formation of columnar structures. So if you take a rotating plank and you put a you have, let's say, a parcel of or if you have a structure that you're moving around, you would see that these fluid structures, they form columnar structures and they do not move up and down. Right? So basically the gradient, so omega dot grad is omega times partial over partial z, for example, the direction of the rotation. The fluctuations along the direction of rotation is suppressed in the limit of very large rotation, right? So this forms this large scale condensate kind of structures, leading to a flow which is almost two dimensional, which is invariant along the direction of rotation, right? And then you can also, if you use some kind of a wave maker, which Mani was talking about, you can also excite what are known as inertial waves, right? So inertial waves is when you have let's say rotating in the rotating frame, you do not have any kind of let's say strong turbulence. What you have is like a quiet state, and then you kind of create some kind of sinusoidal disturbances. These lead to so the natural solution to these would lead to inertial waves, right? So again, you can derive this dispersion relation. So just a quick demonstration maybe is that if you assume that the background velocity field is of the order of epsilon, right? Then what you can do is that you can do a balance between these two terms because the nonlinear term is small. Then you get this linear system of equations. A linear system of equations leads to waves, right? Either they can lead to some instability. In this situation, they lead to waves. So you can again look for plane wave solutions. So u equal to some u hat of k vector comma t exponential, or maybe just k vector pure wave solutions. Yeah. So substituting this relation, so these are plane wave solutions, and substituting this into the linearized equation, so that gives you a minus I sigma. So you have omega vector would be omega hat would be just ik vector curl u hat, right? So you just take the curl of this, it's a linear wave, so just ik vector product. So that gives you ik vector curl u hat, which would be equal to 2 omega dot ik times u hat vector, right? So just substituting the plane wave solutions into the equation of the vorticity field, which is linearized, right? Then what you do is that, so how do you solve this? You again take a curl with ik, or you can take the curl with the original equation, or just take curl with ik, and you can use some vector identities, ik curl u hat would be just equal to minus k square u hat. Maybe just plus k square, I guess. Yeah. So it's double curl of u is just minus Laplacian u, right? So that you can do, and then you get minus I sigma k square u hat would be equal to 2 omega dot ik vector, and again you're multiplying with ik vector. So this equation I had multiplied with ik vector curl, so that gives you ik curl u hat, which is again omega hat, right? Which is omega hat, and then you can substitute this relation. So this relation back here, and that gives you 2 omega dot ik by minus I sigma, right? So then you get I square on both sides, which cancels, and then yeah, so and then you have u hat here, and u hat cancels, and then you get sigma square. If you do this, sigma square would be equal to 2 omega dot k vector whole square by k square, right? So this is a simple derivation for the inertial waves which are present. So we can again look at what are the allowed frequencies, like what Jim and Mani were talking about in the context of internal waves or internal gravity waves. So for these inertial waves, if your k vector is perpendicular to the omega vector, you can see that this product goes to 0 and omega is bounded from below by 0, right? Whereas when k vector is perpendicular, sorry, when k vector is parallel to omega vector, right? So this goes to 2 omega, right? So you can have, so as this figure showed, this experimental image which I took from this experiment which was done at Laboratory the Fast, where they have this rotating tank which drives these inertial waves. You can see that these waves have this particular dispersion relation, and they have this particular range of frequencies, right? Now the question is, what happens if you force these waves very strongly, right? So I made an assumption that the nonlinear terms are neglected, right? So as in I was doing a linearization around the background flow, which is almost 0, right? Very small, right? So what happens when you have these waves which are driven very strongly? So these linear waves can get destabilized, right? And they go to smaller and smaller frequencies through some triadic resonances. So they have some bunch of instabilities that can occur, and these waves, the interaction of these waves can lead to an interesting phenomena which is known as the wave turbulence phenomena. So which is basically a mathematical result which says that if you are in the regime of strongly interacting waves without any large scale eddy, one can use some statistical physics ideas like Gaussian random processes, and write down a closed form expression for the correlation functions, like what I wrote for the 3D turbulence, right? So you can write down some exact theory when you have interacting waves. So when you have a lot of these waves which are interacting in a very random manner, one can again do some analytical stuff, which the lack of time one cannot do here. That leads to what is known as the phenomena of wave turbulence, right? So here is a very initial experiment where they looked at wave turbulence in a tank, and what you see here is the dispersion. So these are the energy content, like what Mani was showing earlier. This is the dispersion relation of this. So these are the energy content across different frequencies, and theta is the angle. So omega is 2 omega dot k vector is the angle which k vector makes with capital omega. So that you can write it as 2 omega, or maybe I'll just keep cos theta. Yeah. So this is the cos theta that you see. So that angle theta is what is shown in the x-axis, and omega is the time component. So you take that three-dimensional field, you decompose the field into these modes, and then you try to find out what is the energy content in each of the wave number and the frequency, right? So once you do that, then you decompose it again. So you write it again in terms of this theta, which is the angle which the k vector makes with omega vector. So you do all this process, and then you try to find out how much energy is in different wave frequencies and with different wave vectors, right? So those get combined into this single parameter, which is the theta parameter. And what they observe is that it falls nicely on this cos theta curve, right? And there's a lot of energy at the zero frequency, which is the large scale condensation that one can see in rotating turbulence. So if you remove this large scale condensation, which was done later on in these more recent experiments and simulations, what they found is this nice energy on this dispersion relation without the large scale condensate. So how do you do that is if you put additional dissipation on these large scale structures by introducing some bottom topography. So bottom friction acts more strongly on this large scale condensates than on these inertial waves. That's what they found, and by doing that, by putting a strong friction, one can remove these large scale modes, which is the low frequency modes, right? So by removing the low frequency modes, you have energy on this dispersion relation, which is basically the dispersion relation of these inertial gravity waves, inertial waves, and you have energy. So you have a phenomena which is close to wave turbulence. So there you can also predict the typical exponents like the Kolmogorov theory, and people seem to have found some agreement. So force rotating turbulence and the current understanding is that it depends strongly how you force it actually. So if you're forcing some kind of strong vertical structures, they become very highly two-dimensional, whereas if you're forcing a lot of waves, they become more closer to wave turbulence, right? But if you force both of them, then it's a very complicated system of interacting eddies and vortices. So vortices and waves, which there's no easy theory to understand them. So this is like the strong turbulence limit in a sense, where both waves and eddies are present, and no easy theory is currently available to understand this particular system. 2D turbulence, we understand a bit at least, maybe more than 3D turbulence, and then wave turbulence also. We have a good analytical grasp on it. Right. So then what happens when you add stratification? So that the effect of rotation was to form this columnar structures. So stratification is if you have a density stratified or temperature stratified fluid which is stable, right? You can have other sets of waves. So the combination of these effect of rotation and stratification leads to this inertia gravity waves, which people have talked about already. If you have the dispersion relation where omega is bounded. So if you have the wave numbers, the variation is only along the z direction, it's bounded from below by f if f is smaller than n. If the wave number is purely horizontal, it's bounded from above by capital N, right? So, like in the rotating turbulence, you have different kinds of waves in this particular system due to the effect of stratification. And this plot was already discussed in detail. So you have the strong dependent. So this is an observation where you see the strong presence of these inertial gravity waves at very large frequencies, and at very low frequencies you have this large scale structures, right? So how do you get to the large scale structures? So this has a phenomena which is similar to the 2D turbulence that we talked about. So one can write down an effective 2D kind of dynamics, which is known as the quasi-geostrophic equations, right? So there's a clear time scale separation between the frequencies of the inertial gravity waves and the frequencies of the large scale eddies. So by doing a scale separation, a time scale separation, right, one can write down an effective theory for the large scale modes. And this one can do again using asymptotic. So first is the large scale balance, which Jim was pointing out. The dominant balance is basically the geostrophy, where the pressure fields balance the Coriolis force, right? So if you just look at the equations and then say that the rotation effect is very large, like what I did here, if omega is very large, right? You just look at the dominant balance. So if omega is very large, f is very large, you have these two being the dominant terms in the horizontal direction, and that leads to the geostrophic balance. And in the vertical direction, you have the hydrostatic balance, right? So, but this such kind of model misses the dynamics. So, how does so given a pressure field, you can find out the typical velocity and velocity fields, and how do you evolve it further, right? So for that, one has to go to the next order in expansion, right? So you kind of do an order by order expansion about the this equation. So that is so you write down a velocity field, the buoyancy term, and the pressure field in terms of an expansion in low Rossby. So the Rossby number gives us the estimate of how strong the effect of rotation is. So when you do a low Rossby expansion, and then you have to rescale these quantities x, the thickness of the layer, and the typical velocities, one has to do a particular rescaling, right, in order to write down the effective equation. So if you do that, so that's again due to a lack of time. So I was asked by Jim to finish by 2:30. So due to lack of time, I will not go into the details, but it's just a simple asymptotic expansion. And at first order, at leading order, you get this dominant balance. And at first order, you can write down an effective QG equation, right? So here we have not considered any effect of the beta plane, right? I mean the variation of the beta along with the latitude, right? So if you add these beta effect of variation of f, and if you add what is known as the unelastic description, right? If the variations of the density is comparable to the background, you can write down a more generalized QG model. So the advantage with that is that given a field psi, right? So there's just a single variable which helps us to evolve the system of equations, right? And this has a lot of resemblance to the 2D turbulence model, where psi. So this is the Q, which is the quasi-geostrophic potential vorticity. There's a lot of resemblance with the vorticity of the 2D turbulence, right? And one can understand why it forms these large-scale structures because of additional conserved quantities and stuff, right? But so this is the picture of the QG. This is a QG picture, and then what happens if you have corrections to the QG picture, as in if you go further in the expansion. So when you have a lot more interactions with inertial gravity waves, then what we see. So this is a figure which was done in Kafiabad and Bartello in 2018. So they have a descriptive image of what happens at very low wave numbers. So these are like large scale structures. So at very low wave numbers, you have a phenomena which is more close to QG, and at very large wave numbers, the system is more or less driven by waves. Right? So there's a clear change in slope at some particular transition regime, and below this particular wave number, you have a lot more interaction of these waves, right? And the question is, can we understand it by some wave turbulence picture, or do we need something more sophisticated to understand? So Jim Thomas is an expert in this, so you can ask him about such kind of models. So then there's this transfer of energy. How do these eddies interact with this background? So how do the eddies interact with the waves, and what is the energy transfer between them? So these are a lot of open questions in this field of study. So with that, I conclude. So most of the geophysical fluids that we see are highly turbulent in nature, right? So they play a very important role in mixing. So you have this anomalous dissipation also, the fact that dissipation is very dominant in these turbulent structures. And so the simplified models like the quasi-geostrophy models, they help us understand some of the large scale structures, right? So energy going to large scales is something that we understand very well. The interaction of these waves, how does one capture them? So that is missing currently in these large scale models, which is basically what all these GCMs try to solve. So how do we take into account ageostrophic corrections? So these are typically mesoscale, submesoscale modeling. So these are left to parameterization. So typical eddy viscosity type parameterization, where you say that the interaction between these small scale structures is related to some background gradient, right? So so the current research is trying to find better closure models, use some machine learning topics, tools to help us do some parameterization. And the kind of turbulence that I talked about is only purely a single phase turbulent with no interactions with any kind of background chemical processes, biological processes, and so on. So I'm sure we'll in this particular school we'll learn more about such things also. So with that, I thank you.
Okay, thanks, Kanna. We can have some questions. So, are there questions?
Maybe I'll do. Yes, good.
So I was curious about what is the effect of confinedness on the coherent structures remaining two-dimensional in your lecture.
So confinement along which direction? The vertical direction. So there's confinement here, which leads to 2D turbulence in the horizontal plane. You're asking what is the effect of this confinement?
Oh, like in the second, the next slide. Thanks. Yeah.
Oh, here. Oh, so here we are using periodic boundary conditions. You put some confinement, there will be some boundary layers, Ekman layers, which by themselves can become turbulent. So they can also introduce some small dependencies along the z direction, right? So they might break exact two-dimensionality by creating some boundary layers where the z dependencies occur.
So, like if there is a situation, like if there are cyclones, then you have Earth is providing the rotation. So in that case,
so you can so basically in QG models, others will know better. So they add a large scale friction parameter, which models this effect of boundary layers. Right? So that dissipates energy at the largest of these large scale structures through these boundary layers, which dissipate. Yeah. So you can add linear drag or quadratic drag depending on whether the turbulent boundary layer, the turbulent boundary layer, laminar boundary layer.
Okay, are there any other questions? Yeah. Yeah, Kanna, can you look at the chat and see if there are
Okay.
questions?
He says structures are coherent is the represented. Yeah, so the question is about what do you mean by coherent, and is it represented in terms of vorticity or other variable also do not change? Maybe the question is about what does coherence actually mean. So basically, it's like the field variables are correlated over a particular length scale and they evolve over a particular time scale without being modified, right? So there's some kind of a correlation between the field variables across a particular length and time scale. Right? So that is what I would call as coherence. So if it is there in vorticity, I would expect it also to be there in the velocity field and other variables also. Yeah.
Sir, how are the inertial waves being generated in the periodic boundary box condition?
So that you can add a time dependent force. So you can create through some elliptical instabilities people have done.
Yeah.
So 1 second. So where do I have that slide? Yes. So I can refer to this article where they have used some kind of an elliptical instability mechanism to generate waves. So this is in the rotating frame. So in the rotating stratified flame also, one can create some kind of time dependent forcing. Jim will know also about it, so you can also ask him.
The coherent structures, when it will interact with the inertial waves, will it somehow break down the structure into smaller particles?
Yeah, so these are again dependent on the regime. So very complicated questions, which I cannot answer with a single line. It should be a discussion by itself. Yeah.
Okay, so maybe we'll stop here and a few minutes break. 2:45 we'll start the next talk. So Vishal will give the next talk. So we have about 5 minutes.